Hello, it's John Saffell and CTO at Alphasesne. Let's now talk about a question. Can we set performance targets for these low-cost air quality sensors? And I'd like to say, yes, we can, but actually it's more difficult and it's more multifaceted than one would first suspect. When we talk about air quality, there are four communities that I wish we all worked together. There's the built environment, that's indoor air quality. There's the urban air quality, which is most of what we're talking about during these sets of lectures. There's the people who focus on greenhouse gases, GHGs, and they're saving our planet. And there are the people who are concentrating on nuisance odors, which are mainly VOCs, the sulfides, the aldehydes, and the ammonia-based. Each of those communities has their own performance requirements, and within each community, it depends on what you are working on as to what your requirements are. For example, if I'm working as a city councilor and I'm worried about the air quality in my city, my question is, do I meet the regulatory requirements? If I'm developing AQ networks for research, or if I'm trying to look at the traffic patterns within my city, then I'll be looking for high spatial and temporal resolution. I want that fine structure, the fine granularity needed so that I know where to make improvements within my city structure. If I'm a scientist, my question is, can the data be validated? How good is it? What are the uncertainties, and how do I define it? If I'm a citizen, why don't you tell me about my well-being? Am I healthy? Is it dangerous to go out there? So each of those sections of the same communities have different questions when they talk about performance. Let us now drill down and look at the actual performance targets for these low-cost sensors. And remember, there are three types of pollutants. There are gases, which are inorganic. There are particles, all the way from ultrafines to pollen. And there's VOCs, volatile organics. And that includes formaldehyde and benzene, but it also includes about 2,000 other VOCs that are prevalent at very low concentrations in our daily life. And the way we can look at these sensors is looking at what I consider the three S's. There's sensitivity, there's selectivity, and there's stability. And the fourth hidden one, of course, is their cost. On their sensitivity, we can look at their limit of detection, the resolution, their linearity, response time, range, the fundamental measurements you should find on data sheets. For selectivity, it is not simple. It is, of course, we talk about interference, but we also have to look at the temperature dependent, the humidity dependence, and corrections, your STPs, that when you're looking at the variation in the environmental. So that's very important in how much those environmentals influence your measurements. And the last one is your long-term and short-term stability. Hysteresis for short-term, long-term drift over months. And that helps you to define your recalibration period, the marketing defined warranty period, your maintenance and your validation. So sensitivity, selectivity, and stability. In the end, we just want the total measurement uncertainty, but it's not easy to come up with a simple number for different sections of different communities. So how do we go about setting performance targets? Well, first of all, we set performance standards. And we start with the people and the scientists who run lab and field trials and report performance in peer-reviewed papers. We also have test houses and certifying bodies, South Coast Air Quality Monitoring, CIRA, CSA. They operate protocols to validate sensor performance. We also have people like the Joint Research Council in ISPRA in Italy. And from a sensor supplier, you can find out from their technical data sheets their performance that they state. But remember, the sensor system manufacturers who integrate those sensors into their cases will have modified the sensor performance, and the raw sensor data is not always adequate for predicting how the sensor actually operates. And finally, we have governments who set directives on what they expect in terms of a very broad brush definition of allowed concentrations. Ultimately, the accepted route for performance validations is through standards committees. The international IEEE and ISO, the localized ASTM in the USA, JISC in Japan, SAC in China, CEN in Europe. They write international, regional, and national standards and guidelines. It's very tedious, but it's very comprehensive, and they set the methodologies for measuring performance. How do you go about getting sensor performance validated? Well, we start with the quality requirements that are set by governments. Then from that, a standards committee is formed, and it writes a performance standard based on how to meet or determine whether equipment meets the quality requirements. And unfortunately, this is not a fast process. I sit on several of these committees, and it takes between 3 and 7 years from start until there is a draft and finally an accepted technical standard. Step 3, a manufacturer goes to a certifying body who will determine whether their equipment meets the standard written by the standards committee. They will sign a contract and they'll undertake testing, which is very expensive and laborious, to see whether the equipment meets the referenced standard. They will also, using step 4, contract a test house to do the actual testing, be it field trials, laboratory tests, or specialist testing. So the certifying body will actually give a certificate at the end declaring conformity or non-conformity to the standard. But we're writing standards. ASTM Group D22 is working on 2 different standards and has just written one for carbon dioxide. Over in Europe, CEN 264 Working Group 42 has been writing now for 5 years a draft standard specifically for measuring and validating low-cost air quality sensors, and we are submitting in December a very long and very difficultly written standard. The simple remit, our scope, write a standard to validate low-cost gas and particle air quality sensors. Problems, is it only in the lab, or do we do lab and field trials as well? Field trials are more realistic but more difficult to validate. And do we write for a single system, or do we write for an entire network? And when we do field trials, how long do we run the field trials? How many units? What time of the year do we run them? And how many different sites? Next is lab testing. Do we go for high concentrations that can be accurately generated, or do we go for the more realistic, very low parts per billion concentrations we see in the real world, but are much more difficult to accurately generate in laboratories? And on the field trials, do we put them next to a road? Do we put them in rural areas, suburban? Do we put them in background urban? We've been talking about outdoor, but what about indoor? There's whole groups writing separate standards for indoor air quality, but it's using the same sensors, with the same electronics, with this very similar data analysis. And another question that's been perplexing us for 2 years: when do we allow the manufacturer to recalibrate units? When they go in for test, those sensor systems may be under test between the lab and field for up to a year. When are they allowed to recalibrate? And the last is, what is a sensor manufacturer doing to that data? We want to have transparency in the data manipulation. On the other hand, the sensor manufacturers want to protect the IP that they've developed in their data analysis. It's a direct conflict. Going from the lab to the field is a big step. It is easier to write a standard that only tests in the lab, where we control all the degrees of freedom. When we go out into the field, we have no control over the degrees of freedom, although I do not recommend air quality networks around volcanoes. There's also a problem that when we define performance, we're defining it on the current knowledge. And for example, in particles, we used to measure PM10, now we measure PM2.5, but the toxicologists are finding that the ultrafines and particles below 1 micron are really the most critical toxicologically dangerous particles. And yet we have no standard, and there is only the beginning of writing standards for measuring ultrafines in air quality in outdoor spaces. That, for example, is a picture in Beijing of the communications tower taken from the same place on 2 different days when there was different concentrations of ultrafine particles. What have we decided from Working Group 42? First, we're going to use both field and lab trials when validating gases, but we'll only use field trials for particles, although ASTM uses only lab trials. And we're going to test in 3 environments: roadside urban, background urban, and rural. And we must test at 4 sites during 2 seasons. So testing just in the winter in the Arctic is unfair. The scope of SEN 264 Working Group 42 is European climates only. However, it is written to be expanded to other climates, and in an annex we discuss that. Last is we ensure that unprocessed raw test data is vaulted and permanently stored in case that there's questions on the validity of the data reprocessing by the manufacturer. And the last difficult problem is we must allow for product improvements, specifically the algorithms for data analysis, but we want to allow it without demanding complete recertification, which can be long and expensive and hold up the natural development of product. Our take-home messages. Each AQ community and their members, they have different expectations of uncertainty. The connection between sensor performance and sensor uncertainty depends on your application. And we need standards. No, they're not there. Yes, they're coming. Those performance standards will encourage improvement of sensors and data analysis, and most importantly, user confidence in the results. So we are looking forward to the new ASTM and SEN standards that should be available soon. Thank you for your attention. I'd like to also thank the many people who have helped us, especially Lek Ampapula, Ick Mead, and other people in Rod Jones's group at Cambridge Chemistry.